So I will begin the studying this book. So basically, there's still many things to change. So I will go over these, and maybe I might have to go very fast, and then you might have to read almost a little bit yourselves. But anyway, so basically, this will be just a teaching course, teaching draft. So the title is Real Projective Orbifold with Ends and Deformation Theory. And we will do, so the conclusion will be for the nicest ones. Okay. The, yeah. So these are the contents. So please read that. So this week we'll cover mostly chapter one, then chapter here as well, and then maybe chapter two. That'll be all. That'll be all for this week. And okay, so I want to do the preface because it's not really understandable at this stage, so I will not do that. Okay, so part one is on the introduction to OE4 and real projective structures. Okay, so here we just want to do some definitions and elementary facts. And chapter one, we basically do uh, some OE4 theory with geometric structures and some linear algebra and higher convergence, group action, and attracting repelling set, and so on. And also some beanbag theory. And then in chapter two, we will review some works that was already done. So by on the Coxto report, and so some previous works we have done here that we'll discuss that. So so to begin with, we will just start with some Hausdorff convergence and affine structure, and then some things on the general theory, also higher convergence theory, and so on. Okay, and so this is on the divisible actions and so on. Uh, so in chapter five, section 1.5, we do the Binbock theory, and so we try to extend the duality to these compact sets, and then also to sweeping actions. Okay, so those are the main things we will be doing. So the preliminary definition is that we begin with RP and the projectivization of Rn plus one. So here you remove origin and you identify all the points which are scalar multiples of each other. And so PGRN plus one acts effectively and transitively on RPN. Sorry, this should be RPN. That's still not done correctly. And so if you look at SV, so if you have any vector space, you can remove the origin and identify any scalar, any things which are positively related by a scalar. Then we denote by these. For example, Sn will be just S of Rn plus one in our identification. And so then here, of course, the projective group is the SL n plus one R, and so PGR n plus one R will be the quotient of this by plus minus one. So this will act on RPN plus n. Okay. So I haven't really going to be saying too much about this, but as we have some notation like CLXA is the closure of A in X, and then PDXA, the boundary of A in X. So it will omit X if X is clear from the context. So if A is a domain of a subspace of RPN or Sn, then we denote by the BDA, the topological boundary of the space, CLA, the subset in Sn, topological closure, and K0 to be for a manifold or orbifold K0 will be the manifold or orbifold interior. So also we may use K0 as an interior relative to topology of P when K is a domain in some totally geodesic subspace in Sn or RPN, and we define boundary A to be of a manifold or orbifold to be just mount boundary and orbifold boundary. Yeah, here. So, so please check these notations are consistently used. And so PQ, given PQ, we denote by PQ the minor are connecting PQ in gray circle if Q is not P minus. So P minus, I denote this is the opposite point of P in Sn. Okay. So if it's not, then this is unique. But otherwise, we have to specify a point on it, not antipodal to both. So we can use something like PGQ, the unique minor connecting PQ and passing G. And if you have PQ in RPN, then we denote PQ denote one of the closures of component of I minus PQ for a one-dimensional projective line containing PQ. So this could be ambiguous. Okay, so in the RPN case, okay. So convex as in RPN or Sn. So you have an affine patch in RPN. So this is the complement of a codimension one space, and it has a canonical geodesic structure where each projective geodesic corresponds to affine geodesic up to parameterization, and conversely, so convex set is a convex subset of affine patch of RPN. And we can use some slightly different definition for Sn. So convex segment is are contained in a gray segment, and the convex. I mean, it has to be gray segment means a segment which contains the antipodal points as the endpoints. Okay. Inside the one-dimensional subspace. So convex subset of Sn is a subset A where every pair of points is connected by a convex segment. So so either convex subset is contained in an affine subspace, or it is in a closed hemisphere, or it is a great sphere of dimension bigger than or equal to 1. Okay. So of course, I mean, this is not exclusive, but just some list. So in the first case, set embeds into convex subset in RPN up to by the covering map. And in other cases, this is not so. Okay. So also affine patch in RPN lips to an open hemisphere in Sn, hence the convex subset of RPN always lips to a convex subset of Sn, which maps homeomorphic under the projection. Hence the convex subset of RPN correspond to Sn contained in an open hemisphere in a one-to-one manner. And of course, so given a convex set in RPN, we can obtain a connected cone mapping to D up to determine up to antipodal point. So for a convex domain in Sn, we can obtain, of course, a unique cone. Okay, so for IPN, you need to make some choices. Okay, of which cone you want to do. So there are actually two cones. So the join of two convex subset A, B in convex domain in RPN is defined as the set of equivalence classes of X sets from Tx plus 1 minus T Y, where XY is in CD and X and Y is in A, X is in A, and then Y is in B, and T is in 0. Okay. So of course, I should remove 0 here. So convex cone means is remove 0. Okay. And also A star B is a set of directions where X, Y is C and D, and X, in A and Y is in B and T is in 0, 1. So here, this double bracket means it's this direction. I didn't really define it yet, but I will use that here. So I will insert something here in the next time. I mean, when in the revision. So this double bracket means if you have a vector x in Rn plus 1, this is the direction of the Sn or the equivalence class containing it. Okay, so of course you don't want 0 here. So a CD is the cone corresponding to this. So once you define have a domain and then you determine what CD is, then you can define these. So this is clear. So normally you will use something like affine T to be affine space, then you know what the join is. So otherwise it may not be well defined. So okay, and the join is in RPN, but join. So this is in SN is always well defined. Okay, but in the RPN is not. It depends on what you choose to be the CD, and we can also use this notation for a point. So P could be just a point. So then you might need to use send notation here. So if you have some set of independent vectors, cones in independent vector spaces, then the sum is going to be sum of convex sets in Rn plus 1 is of the independent space is defined to be just the sum of all these vectors. And the strict join in Sn is given to be the sum minus the origin, and you project to the Sn and then project to RPN. So the projection is Rn plus 1 to Sn and then the Rn plus 1 to RPN here. So we have some classification of cross-convex subset in Sn is either gray sphere of dimension I 0 plus 1 or it's contained in some cross hemisphere and is one of the following. Okay. So of course, this Sn is also in a cross hemisphere, but I distinguish this. So the case is there is some great sphere of dimension z plus z0 or bigger than or equal to 0, and the boundary and the compact properly convex set in an independent subset of SJ0. So independent subspace means that their inverse images are independent, and K is actually just this join, strict join, and so SH0 is the unique maximal gray sphere in K. Okay, so you can find those, and then this is the result, and then or K is a properly convex domain in the interior of some I plus 0 dimensional sphere for some I0. Um, sorry, this should be just I0 and not I. And this should be I0, not plus 1. And unless S is a gray sphere, the boundary K is the topological boundary, and Sn is homeomorphic to a cell. Right. Maybe this should be I0 here because you want to use the some interior of a unique great hemisphere. Yeah. And so for properly convex set, this is again in RPN, this should be the topological boundary, and K is homeomorphic to cell. So I think I should use the smallest Grace subspace containing this. So so S0 is a span of K, then K0 is an empty domain. So the way to prove this is that you take the span of K. So span is the smallest set containing the set, and then I mean the smallest subspace containing K, and then K0 is not an empty domain in S0. And then we take a map from X to the distance of X to K in S0. So this is a continuous function, and you take the maximal point. So X0 is not in K, and if the maximum is less than or equal to pi, then that means that so there are at least 2 points in K cross stitched to X0 of same distance. So if not, then you can move this center X0 a little bit. I mean, some ball with the radius r in X0, and K will only intersect at one point, because if there are no other point, then we can move the center along the segment containing X0 and Y0, Y, and then you can move it away, and then the new intersection can happen in some set of directions away from the direction of that to that point Y of K from X0. Then so then this cannot happen. So because this is a compact ball, so if it happens for all the perturbation, then it will have to still exist in the limit. So this cannot happen. So that means that there's some, if you move all away, then this ball of the same radius is actually disjoint from K, then you can increase the ball of radius. So a little bit. So if there are at least 2 points, then we can find the crossover point K0. So this is contradiction. So therefore, this maximum has to be pi over 2 or bigger than that. So if it's K pi over 2, then you get K is some in some I hemisphere. Okay. So then if you know that these are in I0 hemisphere, then you can all use these work of in the affine work to get the result. And so second part is in some other papers, and I will not do that much. But anyway, you find some great maximal gray sphere contained in K, which must be contained in the boundary, and then you can show that it's a union of J plus one dimensional hemisphere with common boundary. So you can always parameterize. You can show that these are unions of such things, and then there is some independent subspace to that, and then you can project to this space, and then so these will all meet as some convex set, and then this has to be properly convex, and then you can show this is true. This is a join. Okay, so you can go on like this, and so now I'm defining the PB, so I should define this earlier. Okay, and also PGL and R. So I should move this back again. And then I define subspace, independent space, and so on. So I should move that to the beginning. And also we will use something called the Hausdorff distance. So given a set, we can define the neighbor, epsilon neighbor. So these are the set of points less distance less than epsilon. And then in RPN, you can do the same. So given subset, we define the Hausdorff distance as the infimum where K2 is in the epsilon neighbor of K1 and K1 is in the epsilon neighbor of K2. So the distance is defined to be I mean, Hausdorff distance is the infimum of this, and the simple distance is just you choose the smallest, I mean, the infimum of the distance between these two. And these are, of course, a completely different thing, and this may not even be a metric here. But this will give you a metric, and the sequence of compact sets converges to a compact set if this Hausdorff distance goes to 0, and the limit is always unique if it exists, and and also any set of compact sets subsets AI will have a convergence sequence subsequence And because this space is actually compact, and A can be characterized as the following if it exists, that A is a limit point of some sequence in of AI in A. So you look at all the points in maybe I should not say maybe I should just say this is Sn. So limit point of all the sequence of the points. So if it exists, then it has to be this set. And this is of course this is proven in some other book by Benedetto and Petronio for the Shabati topology, but the Shabati topology for compact space is Hausdorff topology, so you can use that theorem here. And they furthermore prove that, of course, this is not their result, but they prove in the book that a sequence of compact sets converges to A in Hausdorff topology if the both of the following holds. So if Xi J is an Aij and Xij converges to X, then X is in A. If X is in A, then there exists Xi in AI, so that Xi goes to AX. So again, this is proven for Shabati topology. Again, that's it applies here. And and of course, if you have some convergence sequence of elements converging to GX, then KI is converged to K, then their image GI KI also converges to G infinity. So for example, you could make this constant. So for example, if you fix G, then the will also have. So also you talk about the hemisphere converging supports a domain if H contains D, and then H is called the supporting hypersphere, supporting hemisphere, and an oriented hypersphere supports a domain if the cross hemisphere bounded in inner direction by S contains D. So this is called the supporting hypersphere. And the sharply supporting ones are ones that contains some point in X, D, I mean the boundary point, and so on. Okay, so from this you can prove that if Ki is a sequence of compact convex sets, then up to choosing a subsequence, you can always make it converge to a compact convex set. So if these are cells, then the end has to be a cells, and then so I mean the compact convex cells will converge to compact convex cell. So the geometric limit must be inside the compact convex cell when Ki is a compact convex cell, and K is in a fixed hemisphere, then so is in K. So also the following is well known. So if each Ki is a compact convex domain, then K is one also. Of course, it could possibly have a lower dimension, and K is a convex open domain, then K is also one in K. So this is only when K has the same dimension as Ki, and K is a properly convex domain, then K is also properly convex here. But of course, so suppose this condition holds, one of the three condition holds, then the closure will converge to K, CRK with non-empty interior, then the boundary also converge. Okay. So that has a sort of bit of long proof, so we'll skip that. Basically, you have to just check what are the boundary points. So the main point here is boundary convergence. And so next, if K and K are properly convex balls of same dimension as Sn, and if it converges to K, then boundary also converges. Okay, and if it's properly convex, then it works. So uh, okay, so prove that here. So also we need to look at Hilbert metric. So let's look at OSQP. It's also cross ratio 4 points like this. So suppose these are all distinct, and so where this denotes the first coordinate of the homogeneous coordinate, provided the second coordinate equal to 1. So since this is online, you can always use the two variable coordinate, homogeneous coordinate. And the pseudo metric is for any convex domain is defined as log OS PQ, where OS are the endpoints of maximal segment containing PQ, and OQ separates PS. If omega is properly convex, then it is a metric and it's Winslow metric. So if it's a complete affine, of course, the metric is 0. You can always, because O and P are the same. So if you have O and P are the same, then you get 0 here, and then um, now O and S are just the same. So you get this 1, so you get 1, so the log is 0. So if Ki goes to K geometrically for a sequence of properly convex domain, then there are two sequences converging to XY respectively, then this distance converges to this. Okay, so that's another fact you want to know. And so another fact is, so if you have some convex domain, subset of properly convex domain B, then the set of points which are of the distance less than epsilon, then this is again properly convex. Okay, and omega is a properly convex domain, and the group of automorphism of the fixed omega is actually closed in this as a subset subgroup, but this is not a this is always going to be some discrete one, so with dimension 0, and a set of elements such that so sending some compact set to points to some images in some compact subset of omega is also compact. Okay. Okay. So this argument you'll have to do some geometric with the simplices and so on. Okay. And so we'll also talk about topology of orbifolds. So we have some so we study orbifold, so I will not talk about that. And the sub-orbifold is so there are some mistake here. So you need to use phi inverse here to get this right. When the phi is a chart, and so please read about orbifold covering and so on. And so we can always give some Riemannian metric on O, so that boundary O is totally geodesic, and neat manifold is always perpendicular. So we did cover this in the first half. Of course, we don't want to do it anymore. And again, and so also we did geometric structures in the first half, so we will skip that. And the real projective structure, for that, we want to study these cones, and vector B is the equivalence class, and pi denote the projection, and so on. And so I think this should go to the beginning, but I think this was repeated because I moved things around so many times. So I think I will move this again, and so I will. So there are some notions of these kind of things. I should okay. And the affine group is the group of projective automorphism fixing on affine space, and think about the developing map and so on. And okay, and we want to do spherical. Yeah, so you want to do a spherical. Spherical structure. You just need to instead of developing to RPN, you can always lift to SN, because this is a O tilde is simply connected manifold, and so under the covering map you can always lift. And this lift is always unique up to some antipodal map. So so these will be developing maps. So you can always lift the holonomy to SLN plus 1R, not just there. And so actually the so space of just real projective structure is same as the shape of spherical real projective structure because of this lifting. And and the set of this type of diffeomorphism is also the same. And so because of this fact, you can use the fact that the holonomy group of convex real projective structure is real residually finite, because you can always lift to this embedding, and then you can lift it to embedding to SN, and then any automorphism there is going to be in the subgroup of SLN plus 1R, and then so this is a linear group, so you can use Marsev's theorem to show it's residually finite. And this Selbach theorem can be applied to show that any real projective orbifold is finitely covered by some manifold with a finite group here. And and for the affine manifold, you can do the same. Okay, because once you lift, then you can always apply these Selbach lemma and so on, and then you can do this kind of thing. And also you can, so I will skip this one. But essentially what it says is that you can always lift to oriental. If it's orientable, you can lift so that these are go to SLN, not plus minus, but SLNR, and it's not orientable, then this deck transformation goes to negative determinant matrix if it reverses orientation, and if not, then goes to positive determinant matrix. Okay, so that's kind of thing. And you can so if you have any convex domain and subset, then you can always define a convex hull inside. So so this is the smallest set in which contains this smallest convex subset containing this. Okay. So as long as omega is properly convex, it is well defined. But if not, then it might not be. Okay. Okay. So okay, and then finally, I have this Ki is a sequence of convexes in convex property domain for each I. Then it converges to a compact set, and this convex hull will also converge. Okay, so so to do that, you need to write this as some in this way, and then you will have to use the so some geometric theorems like 1.17 here. So let's see, 1.17. Okay, so 1.17 was, yeah, this Benedetto theorem. Okay, so so this is the first half, and then I will begin with this next.